Hi, everybody. It's our pleasure to welcome you in this second AMOZONE webinar. It's really great that you are here. We have, again, people from all over the globe attending from different continents, different time zones. So yeah, it's really great to have all of you attending. All of you are water professionals, or at least most of you, and also involved in advanced oxidation or ozonation. So we have collected a huge amount of information for you. So the webinar, again, we have 1 hour, will be quite dense. But yeah, luckily we have some space to also have some question answering. So welcome in this webinar, Ozonation 2.0, application of the new AMOZONE model at different plants, at different full-scale plants around the world. So what are the objectives of today? Well, let's first put things a bit in a context. So AM Team, our company, I will very briefly introduce ourselves. AM Team is currently deploying the AMOZONE model, which is an engineering simulation model for ozonation and advanced oxidation systems at the international scale. What are the objectives of today is, well, that you get some new, really detailed process insights that really were difficult to get without simulation. You also get some more basics of the ozonation process simulation. So what is process simulation? And also that you understand the practical application and the potential for process simulation for optimization, design, and monitoring. And especially the monitoring that's quite new. For example, if we look at bromate target contaminants, they cannot be measured online with a sensor. Also, offline measurements are very difficult. And we, with this model, also wanted to focus on that. What is the format of this webinar? It's a hybrid model. So we have a presentation of irregular slides like the ones here. And then we also go to live demos. And we go to our colleague, which I will introduce later. There is a question possibility, Q&A. So if you hover over your screen, you see a Q&A button. It's not the chat, but it's the Q&A. If you have questions, write them down there. And then our moderators will be looking at them continuously. And we can answer the most interesting ones or the most relevant ones live in the webinar. Important, after the webinar, there will be a questionnaire. It would be really great if you could help us improving and share your feedback on this webinar. Good, so how does this webinar now look like? First part is introduction, very short. It's only 2 slides on personal introduction, who are we? And then some ozonation and simulation basics, because those are very important in order for you to grasp the remainder of the webinar. Because then we go to the real stuff, which is really the virtual experimenting and the virtual piloting at full scale, or let's say real facilities. We will go to some batch studies. We will go to virtual piloting, where we try to replace real piloting by computer simulation. And then we also go to virtual experimenting, where we start playing with an existing full-scale plant. So let's start with ourselves. We are AM Team. AM Team is a company headquartered in Belgium, but we work for customers all over the globe. You might recognize some of the logos on this slide. And also on the world map, you can see that we are working with a huge amount of different time zones. So luckily, simulation activities don't really suffer too much under time zones. So we work remotely for the whole world. We are uniquely specialized for CFD, computational fluid dynamics for the water industry, but we are also quite specialized in kinetics. And the kinetics is a big topic today because we have been developing in-house a new model, a kinetic model for ozonation. We are quite unique at the global scale due to the unique combination of our very good, let's say, very leading edge simulation capabilities, very good software, hardware, and also expertise, combined with a laser focus on the water industry. So we go really deep in the process knowledge. 3 types of customers and users. It can be utilities, but then we have the engineering and consulting firms and also technology companies. So we also help technology companies with technology scale up and also technology improvements. Good, last slide. This is our current team. It's growing quite fast the last year, let's say. So very, very cool team. a lot of simulation passionate people, and all of them are actually engineers from different backgrounds. Our customers are generally something we put on the slides, customer ratings, because we are quite happy with them. Why? Because as a simulation company, you only have, let's say, one reason for existing. And the reason is if you offer practical solutions that work, that solve practical issues. So our customer ratings are really something that are the proof of that. But that's enough sales talk. I think we have to go to the webinar. And these people that are now on the slides are the ones that are involved today. So we have myself, I'm Wim Oudenaert. I'm CEO and co-founder at AMTeam. My main background, I did my PhD actually on the topic of ozonation and advanced oxidation modeling. And then we have been working on it for the last couple of years again within this company. And then we have Roberta Moyo. She's now calling in from Italy. So she will be co-moderating this webinar together with our colleague Celia de Wilde. Celia is Business Development Manager at AMTeam. And then we have our simulation expert in the ozonation field, Giacomo Bellandi. He's also from Italy and will also be, he will be showing a lot of stuff in his screen. So we will see him from time to time. Our first webinar full recording is available online. So if you go to amteam.com/AMOZONE, well, then you can find 1 hour recording of the first webinar, which has information that we will not be showing today. Okay, let's start with the most interesting parts on the kinetics, on the ozonation process. And let's start with a kinetic fact. A very important kinetic fact is that if you want to remove targets, and targets can be target contaminants or target organisms, they are removed by both or deactivated by both ozone and hydroxyl radicals. But this happens at very different rates. So this means for different pollutants or target organisms, you need different exposures, different concentrations needed, or also time. And that's quite important because in the end, we want to get some oxidation, some destruction of molecules. And this is something really that we have to account for. Based on our experience, we have seen that not many people really grasp this concept quite clearly. So this is why we will start with this. Just look at the reaction rates here on this slide. It shows for 5 organic molecules, only just 5, the rate constants with hydroxyl radicals. And they are very high. Just look at the numbers. The minimum is like 1 million, 10 to the 6th. And we have components that have a reaction speed of 10 to the 8th, 9, 10. Very big numbers, very fast reactions. We all know that hydroxyl radicals are very reactive and that the speeds of reactions are very high. But let's look at the ones for ozone. And then that's a different story. You can see that, for example, diclofenac and carbamazepine have very high rate constants. Diclofenac has an equally high rate constant with ozone than it has with hydroxyl radicals. So it's a very reactive molecule. You only need a tiny dose of ozone to get it completely removed. If you look at the other extreme, 1,4-dioxane, well, this almost exclusively reacts with hydroxyl radicals. So if you see a removal of 1,4-dioxane in your system, there must be hydroxyl radicals in your system, even though if you only dose ozone, for example, without peroxide. We typically compare it with skins. For example, the left one has a very sensitive skin. For me, for example, look at me. If I go to the beach and I have no protection, I'm like diclofenac. I will get red very easily. And then you have other people that stay in the sun 1 hour longer and you hardly see it. So that's 1,4-dioxane. So you can compare it with different skins, different sensitivities of the molecules. But let's go to Italy now for a demo. And I will stop sharing my screen. And Giacomo will now continue and he will go to a batch experiment, giving really examples on how this works. Giacomo, the floor is yours.
Yes, thanks, Wim, and welcome everyone again. So what you see on your screen now is the simulation platform Sumo from Dynamita, in which we implemented the AMOZONE model. In here, you see the model layout. So the conceptual layout of the model, you see two beakers in which we put some surface water or secondary effluent from as if it would be coming from exiting from a wastewater treatment plant. Instead, this surface water is like normal river or lake water. Here below, what you see, it's a plotting section in which we're looking at concentrations in function of time. And what happens if we are going to dose some ozone, like 5 milligrams per liter shot, only once into one of these beakers. In the one surface water, for instance, we can simulate the depletion of ozone in time, describing all the reactions with organics, with the water matrix in specific. So all those compounds like carbonaceous substances and so on, organic and inorganic substances, which will interact with ozone. And what you see here, it's a typical profile of ozone in a surface water sample, where alkalinity and organic content, it's rather low as compared to a secondary effluent, for instance. And you can still observe a first very fast reaction of ozone, where the concentration drops very, very fast towards, downwards to lowest concentrations, and then it slows down and reacts slower and slower. This is the consequence of ozone reacting with UVA, so the fraction of organics. So it's a matter of describing organics in solution, and the UVA fraction is depleted very fast initially, because the easily breakable molecules, organic molecules, can be degraded very fast, and then you have the die-hard part of the organics, which takes a bit longer. But so what we can describe in this with this model in the matter of milliseconds, we can also look at the production of radicals. And this is the most important part, as well as ozone concentrations and levels, because this is leading to the local concentrations in your reactor, which will allow the removal of certain compounds. Like we were seeing carbamazepine and diclofenac. Let's zoom in there. So you see that here, carbamazepine, it's depleted in few milliseconds, only basically by ozone, because it's very sensitive to ozone. It's very sensitive also to hydroxyl radicals, and the combination of both makes carbamazepine, but also diclofenac, react very fast in this part. So what you can also observe is that some other compounds like metformin will have some, you will not be able to remove them all. Why? Because at some point your radicals will be limiting, and at that point your metformin will not be sensitive anymore to since it's not sensitive to ozone concentration, but only to radicals, then it will remain in solution, as well as, well, on the other hand, the metoprolol, the brain is sensitive reasonably also to radicals concentration, and a little less to ozone levels than carbamazepine and diclofenac. Then it will take a bit longer to be depleted, to be disappearing from solution. Why? Because yes, the first initial fast drop in the few milliseconds is largely thanks to the hydroxyl radical concentration, but the residual ozone will knock that down until zero. All right, then we'll go more in detail in the next demo session, and I'll give the word back to Wim.
Okay, so we will continue. So if you have any questions, just ask them on the Q&A, and our moderators, Celia and Roberta, will be looking at them, okay? So don't hesitate to ask questions. So what Giacomo has shown now very clearly is, if we look back at this slide, diclofenac has a very high rate constant, 1,4-dioxane, or metformin, for example, very low one, and it has huge consequences in the removal speed. But this also reflects on, of course, immediately in how do you design your system, and which dose do you need to remove certain target contaminants. So it has a huge impact. Of course, which components you have in your water are one thing, but then the type of water you have, that's the second very important factor. So the levels of both ozone and radicals are completely dependent on your matrix. So this means if you look at surface water, wastewater effluent, or even waters after RO, you have some people in the food industry, or you have other industries as well. For example, aquaculture that apply ozone. Well, it all looks very different. So let's look at this kinetic fact, so the matrix. This is on the slide. What you see here is a simple banded pipe. It's a pipe, and ozone is dosed at the start, and it flows out to the right. It's 4 times the same pipe. But what we visualize at the left is secondary effluent, let's say a very reactive matrix, and a less reactive matrix at the right, which is, for example, drinking water or surface water. The top row shows the local ozone concentration, and the bottom row shows the hydroxyl radical concentration locally in this pipe. So this is a computational fluid dynamics simulation. To be sure, it's a 3D pipe. Well, what you can see is that ozone depletes very fast in secondary effluent, while it survives way longer in drinking water, of course, leading to much higher CT value. Yeah, obviously. Look at the radicals. It has a huge impact as well, because you produce quite some radicals in the beginning, while in drinking water, you also have some radicals, but the levels are generally much lower. So this is the impact of the matrix. So if we now combine it, the matrix, with the reactivity of components, we get these kind of plots. And here we visualize the same pipe, but we compare 1,4-dioxane with diclofenac, for example. And what you can see is, in a very reactive matrix where you produce quite some radicals, you have significant removal in 1,4-dioxane, but let's say you get until 40% removal or so. For diclofenac, it doesn't matter. It is 100% removed after a few milliseconds to a few seconds. And this is what you clearly see here. Red is 100%, and it's already dark blue, even at the start of the pipe. While in drinking water, it's much more difficult, this one. In this case, so it's very matrix dependent. But we are just visualizing here, if you have a pipe of, let's say, 1 meter of length, well, this is the consequence of your removal of target pollutants. And the third one that is very important is bromate. If we are looking at ozone, bromate is always a variable of interest. In the end, you go from bromide to bromate. Just neglect what is in between here. It's quite complex. We will not show too much here. But just remember that there are 2 pathways. Bromide either reacts with hydroxyl radicals, or it does with ozone. And this leads ultimately, via a few intermediate steps, to bromate. So again, this is very important. So we will now go back to Giacomo, and he will go 1 level deeper with the batch now, starting to compare 2 very different waters.
Yes. So let's go a bit deeper in the story. So what you see here is, again, our 2 beakers, in which in one we have surface water. So like, imagine it very clear, low organics, low ammonia, almost none, and low alkalinity, and so on. And a sample instead in the second beaker with secondary effluent, with quite some more organics left over from the upstream wastewater treatment plant, some ammonia left, some nitrite, some nitrate, and so on. So what happens to the profile of ozone? So here we have the profile we have just seen of the surface water. Let's look at the secondary effluent ozone profile. So as you can see, in few seconds, in about 6 to 10 seconds, the ozone gets completely removed. So it reacts with the water matrix, and it gets depleted much faster than in the surface water sample. So let's look now at what happens in terms as a result of all these reactions with organics and inorganic fraction of the water matrix. What happens to the hydroxyl radicals? So we have seen our radicals generated in a matter of milliseconds in a peak concentration here from the surface water sample. And here we see again also the secondary effluent concentration of radicals. So as you can see, it's much lower. And the reason why this is much lower, it's a consequence of a very complex net of reactions in which you have higher production, but also higher scavenging at the end of the story of hydroxyl radicals. So you do produce more radicals because the reactions are faster and imply a larger amount of ozone consumption, but you also scavenge more because of more inorganic carbon content or more organic carbon content that does the same job, and so on. So what is this, the consequence in UVA? We see it here that our UVA content in the secondary effluent sample, it's generally much higher than the surface water. So you have more organics to destroy, but most importantly, what happens in terms of micropollutants. So if we look at the carbamazepine and diclofenac profiles, and we add the profiles with the small dots regarding the secondary effluent, we see that they're disappearing still in the first few milliseconds to seconds in our beakers, because they are very sensitive to the initial ozone concentration and both also the radicals. So keep that in mind. And what we can look at here as the difference between the diclofenac in surface water and diclofenac in the secondary effluent. So they practically behave in the same way because it's due to its very high sensitivity to ozone and radicals present. Carbamazepine also reacts in a very similar way in both samples, slightly slower one, if you can say so. It's really a matter of milliseconds here in the secondary effluent sample. But the story changes if we look at metformin. Metformin is very, very sensitive only to radicals, not to ozone, and the residual ozone doesn't have almost any impact on metformin. And the fact that we have less availability of radicals because of the higher scavenging in the secondary effluent sample makes metformin really difficult to be knocked down in the secondary effluent. Finally, if we look at metoprolol, the picture is even more different here between the surface water sample, where metoprolol was removed just as a matter of time, because that is still sensitive to ozone, other than to the radicals. But what happens in the secondary effluent sample is that ozone gets depleted in the first, remember, in the first 6 to 12 seconds here, the aqueous ozone in the secondary effluent, it's consumed, and then as a result, you have micropollutant residuals. So you are not able to remove it anymore. And also the radicals are gone as well. So finally, we can look at the bromate levels, which look very different also for the surface water sample and the secondary effluent sample. So what is the difference? The main difference here is that as a result of a very complex and long list of reactions that end up eventually in bromate, very important is the availability of radicals to trigger these reactions and the availability of ozone. You remember what Wim just mentioned about the two ways of starting up the bromate formations that you can have, either way with radicals or with ozone. Well, in the secondary effluent sample, you have limited possibility there because both are being depleted very fast. So this is mainly what is about the difference that we are observing here. And now, before we go more in detail, we go back to Wim and we see each other shortly for the next demo.
Maybe Wim, if I can jump in, there have been some questions. One of them is if we assume complete oxidation or if we also look at the breakdown products. And the other one is concerning the previous slide with the pipe. If there are more hydroxyl radicals and ozone in the drinking water pipe, why is the contaminant on the top of the previous slide not removed? So maybe you can quickly answer those two questions before continuing.
Okay. Yeah, very relevant questions. So the first one is a question we get more and more often. We didn't expect it because we expected that people in the first place would be focusing on the target contaminants, but indeed more and more people are concerned about the byproducts. And the good news is, well, they are not currently in the model because we have been focusing on the first priorities in the market. But we definitely have plans to include some breakdown products because so much nice research has been done. And for many of these target contaminants, the yields and also the production rates and which byproducts are being formed, they are known. So we can easily extend our model with it. So that's definitely possible. Second question, well, it is important to notice that the slides, well, the simulation Giacomo has shown, comparing secondary effluent with drinking water, they were completely different matrices than the one in this slide. So it's highly dependent on the matrix. So let's not generalize that you have more radicals in drinking water compared to wastewater and reverse. It really depends on the case. In this specific case on the slide right now, you had actually either a lower production of radicals or a higher scavenging of radicals in let's say the less reactive matrix, which is the drinking water. Yeah, this is what you can see here. So it's really matrix dependent. We can give the definite answer definitely if you send us an email. Then we can really say it why it's happening. So let's conclude on this kinetic side because then we go to probably the most interesting one, which is piloting and full-scale application. First conclusion is the removal of target contaminants or organisms is dependent on their sensitivity towards ozone and radicals. So just think about the skins again, very sensitive versus very resistant, let's say. And then also the levels of ozone and hydroxyl radicals are highly dependent on the matrix. So these are really, really very important things that drive how ozonation or advanced oxidation will perform. Good. So what is a process simulation model? Because Giacomo has already shown a batch reactor. It's actually very similar to a real batch reactor in the lab. You just have inputs and you have reactions going on. So first input is water matrix data. It's DOC, COD levels, conductivity, your target contaminants, bromide levels, of course, very important, and things like that. pH is also in there. And then you have other things, which are your process settings. This is what you decide upon. Which ozone dose do you use? Do you use chemical dosing? For example, do you add peroxide? What are the volumes and the flow rates you are going to treat? Things like that. So this is engineering questions The left one is actually the water matrix questions. You feed them to the process, which is also done in reality, but except from a real system, you now have also conversions going on, but they are written down in some mathematical equations. We will not go into detail, so this is the only slide showing mathematical equations in this webinar, but it's good to understand because you can see the dc over dt describes the change of a concentration as function of time. For 1,4-dioxane, for example, it is minus. This means 1,4-dioxane will start being depleted throughout time, while bromate has a plus sign, which means there is a production going on, which is written down by many chemical equations. And in the end, what comes out, just like with a real process, is the ozone decay, the removal of target contaminants, the bromate formation, disinfection, and things like that. So it's very similar, just make the reasoning that it's very similar. And then when can you apply models? Well, we have seen that you can actually potentially apply them in 3 very different application phases, let's say. The first step is when you are deciding on the technology you are going to select. For example, will ozone work in our specific case, and which dose would we need to reach a certain goal? Typically, many people start doing pilot trials, and the pilot trials are quite costly. They take long, and we think they provide limited learning compared to also complementing it or having them replaced by computer simulation. Step 2 is, okay, when you have decided to choose ozone, you have to design a process. Well, it's not always easy to design a process. For example, reactor sizing, what is the residual you are going to get? There are many design challenges. And then finally, when you have designed your plant, you have to build it and then start operating it and monitoring it. And the pity is that you have no sensors available for monitoring of target contaminants and also bromate. So we believe that simulation can also add a lot of value there. So the answers we wanted to actually bring with our model were, okay, depending on the matrix, what if we would have a simulation model that would really predict ozone, radicals, bromate, and trace organics, and also as function of process settings. So this would be plant independent, very important. So this was really the main core question. Let's go to a first case study where we did virtual piloting in the technology selection phase. So our customer Waterboard De Dommel in the Netherlands, some of the people are also joining this webinar right now. They had the question, well, if we go for ozone, what would be the dose we need? How much bromate would be formed? What would be the cost implications for us at this specific plant? In the Netherlands, there is a lot going on right now, also in terms of regulatory developments. For example, they already have a list of 11 indicator components from which you have to remove 7. And but also, yeah, there are other questions. For example, what if the regulation would change in the future? What if it would become 18 indicator components and we have to, for example, remove 11? Can we do some additional testing? Waterboard De Dommel didn't really feel like building quite an advanced pilot on site, so we went for the simulation route. How did it work? Well, we started collecting some on-site data offline and online. Online means pH, ammonia, which is already there, and also UV254, for example. Offline means DOC, nitrites, carbonates. That's step number 1. And step number 2 was taking a couple of samples on site, and you can see it on the picture, where 3 of us have been on site, and we had collected a sample, which is in this box, sent to a lab for some basic ozonation tests on which we calibrate our model. So if we then feed the calibrated model with the real-time sensor data, we can start the virtual piloting. And in fact, it's not really a pilot. You can build several full-scale plants. So we have built several virtual full-scale plants that were then fed with the real online sensors at the plant. There's one big difference, of course. No plant has been done here. And also, there was not a single micropollutant analysis needed. So that's really key here. Some inputs we got, flow rates, ammonia, DOC profiles. This is a typical day profile. Of course, we did some longer data collection, but this is just one day, 3 a.m. to 3 p.m. You see the flow increasing in the morning, These are the typical patterns observed in wastewater treatment plants. On the other hand, if we look at the lab calibration, this is some of the data. You can see the ozone decay very fast, and then it goes down, and at a lower dose, which is still high in this case, by the way. But it's just to illustrate that we have done some calibration. And again, we come to the matrix here, very matrix dependent. And then we did some validation, not really calibration, because our model didn't need any calibration for bromate. So here you see the bromate being formed as function of time in a batch experiment in the lab, and the model is quite nicely predicting the levels. So at very, very high doses, we are talking about even 20 in this case. There are different runs were done, but with a dose of 20 of ozone, you have around, in this plant, around 15 micrograms bromate, which is still low if you look at the ozone dose. But yeah, let's go back to Italy, because Giacomo has a lot of interesting things.
Wim and Giacomo, I will just jump in again. If you could answer a question, if you also include gas transfer efficiency, etc., and bubble size when we are looking into ozone efficiency. Yeah. Or if we start from the point where ozone is already dissolved. I think this is an interesting question to answer. Yeah.
That's a very good one. No, indeed, in full-scale plants, we typically start with a transfer. That's very important. The batch experiment Giacomo has shown, well, we just added virtually ozone from a stock solution that was already dissolved. But of course, if we go to plant modeling, gas transfer is accounted for, KLA, bubble size. And we also look at side stream injection bubble columns. This is less of details today in this webinar, but it's definitely something we have to consider, because it has a huge impact on the kinetics.
It needs to be included, indeed, because it's a crucial point. And speaking of which, let's go to the virtual full-scale installation of Waterboard De Dommel. So the model as you see here is running on an influence of flow rate, UVA, DOC, lots of, it's a nice set of 1 month long data, actually even more, which is has been measured at the outlet of a wastewater treatment plant. So here you see the influence of our ozonation plant, which is the effluent of the upstream wastewater treatment plant. What you see here, the effluent wastewater from the treatment plant is arriving to a split, which is a bypass where the high peaks in outflow are bypassed into the overall, plant effluent. But most of the flow is directed to our ozone installation. That's sized, which is sized to treat most of the water flow coming from exiting the wastewater treatment plant. Now, the first thing that we encounter here, it's another split, which is directing 20% of the flow to our side stream injection device. So in here, you have the gas transfer of the side stream injection, which very efficiently injects ozonated gas at a certain concentration, depending on the generator in use, and is controlled, can be controlled with different control strategies. Here you see different examples of controllers, like a flow proportional controller, DOC proportional control, even micropollutant-based controller, because that's the next step. We can look at it later, basing your actual dose on a specific micropollutant to be sure to be in the legislation boundaries. And also another one, the UVA proportional controller, so ensuring that parts of the UVA fraction is knocked down, and basing on that your ozone injection. So after the side stream injection, after injecting your needed ozone, then you re-enter the mainstream and you let react in your volumes and the rest of your installation let the reactions happen of ozone, radicals, micropollutants reaction, bromate, and so on, until you discharge. And with this model, you can go and look at the what is happening inside your installation. Actually, what is the effluent bromate, for instance, at different points. And what is interesting here to see, it's also what Wim will talk about later, will mention again, is the ammonia relation, the ammonia influence on bromate, because of the formation of monobromamine and dibromamine, which is sequestering bromide ions. And this is an interesting detail because it really influences the bromate formation, and meaning that the control of your upstream installation, the wastewater treatment plant, has an impact on your bromate formation possibilities then. But also you can check the UVA fraction that is exiting the plant and the overall effluent at the outlet of the whole plant site. So what I was talking about, you see this red line here is where the bypass kicks in. So this is well, a reasonably small rain events, but which caused a sufficiently high flow to get bypassed here. And here is the capacity of the ozone installation treating all the rest of the days of the flow during the rest of the days. So what is interesting to look at is the amount of the micropollutants. Here are listed the interesting ones for Waterboard De Dommel, and you can look at how they're removed in time in the different days of simulation, depending on as a result of a whole complex net of reactions generating and balancing ozone and radicals concentrations. What you see here is the relative removal of the compounds. It's mostly what regulations look at, and the ones that you see at the top here are the ones that are removed, let's say, better or to a larger extent. You see mostly the ones that like diclofenac and carbamazepine that we have seen earlier, sensitive to both ozone and radicals, you will find it easily here. Whereas the more you go down, and the more you find like recalcitrant, more resistant and die-hard compounds like ibertazan. Nonetheless, you can monitor crucial variables that will be useful and very important to size your real installation. And based on this prediction, you can actually think of really know which one is the generator that you will need, the size of your installation, to make sure you won't have residual ozone in the effluent, but also you won't have oversized your installation and your capex as well. So you can look at the ozone dose, the ratio ozone DOC, the average micropollutants removal, and so on and so on. So now we go back to Wim presentation, and we'll see shortly for the last part of the demo.
Yeah, maybe Wim, before you continue, there were a few questions. I see you answered one about calibration already, and then there's also a question how we did it for the micropollutant influent data for dynamic simulations. How we cope with that.
Yeah, so the thing is, it's maybe hard to understand. We have limited time to explain all of this in this webinar. But actually, to run this model, we don't need the absolute concentrations of your micropollutants. The model, in either case, will always start even without micropollutant data, it will always give you the relative removals of whatever component you have. So because the micropollutant levels in such matrices have no impact themselves on ozone consumption, for example. We are not talking about industrial wastewater here. We are talking about where there are trace organics. Yeah. So, and then on the calibration, that was also a relevant question. The question was, how do you calibrate for different plants? Well, currently we have two options. Either there's an existing plant with data. Typically, we can work with the existing data to calibrate the model. If the plant has not been built yet, for example, in this was a good example in the Netherlands, then we send some lab samples, some samples to the lab. But even in many cases, yeah, where we have no data, based on a lot of experience, of course, after a while, we can always fill the gaps. Yeah. But again, matrix dependency is very, very important. Nice slide illustrating what Giacomo was explaining this one. This is just one day out of this whole month Giacomo was showing. But you can see typically in the morning, ammonia peaks, aeration with the ammonia-based control goes up and ammonia goes down, almost hitting zero. When ammonia almost hits zero in the morning, well, let's say right afternoon, you can see that bromate might spike. It might spike. Why? Because yeah, you have always some mono or dibromamine being formed. And if this is formed, it cannot form any more bromate. So it's actually good you have always some ammonia in your water. But this is causing very interesting things. Typically, you would never see this if you do regular sampling, because if you, for example, take a 24-hour composite sample, you will never have observed this. And we have checked this with literature as well, where people investigated the impact of bromate and ozone and ammonia levels. And you can see that actually our predictions are nicely matching with what has been observed in rather fundamental studies. But this is the most interesting part, of course. If you have this virtual full-scale installation, you can just release the model, and in a matter of a couple of weeks, we have tested all kinds of scenarios, different dosages, different dosing strategies. And then for each of the scenarios, you can make, for these 11 Dutch indicator components, the analysis of how much are above the 70% threshold, 8 to 7 to 10. It depends on the dose, of course, but you can easily visualize this and then, of course, make an analysis of this. Again, what if the future regulation would change? We have 19 instead of 11 components. We just add the components, and then you see the extended set with the same scenarios here. And then you can look at 70% or maybe future 80% target removal percentages. So this is the combined flow of both the bypass and the ozone plant. Of course, you can visualize both. And in some of the scenarios, we assumed 10% removal at the biological site. And in another scenario, more, let's say, best case, we assumed a 30% removal. In reality, it's somewhere in between. Of course, interesting output of such an exercise, including flow rate changes, is what is the kilograms per day of ozone you need in all of these runs? And also, what is the OPEX? What is this OPEX plus investments you have? And also, yeah, for example, in cents, euro cents per cubic meters. Quite high at this plant because it's a very small plant. But you can visualize all of these things and also then start playing with your dosages. Conclusions of this study were, well, the cost and time for real-life piloting would have been orders of magnitude higher. We are now talking about 6 weeks. If you would have put a pilot on site, we would have easily talked about 1 year or more. We are not saying that on-site piloting is not valuable or cannot be valuable, but we have observed that in many cases, the value can be better or the process can be much more efficient. So yeah, also ballpark costs wise, it's very different. Huh? You are talking about like 10,000 or a couple of tens of thousands of euros instead of hundreds of thousands of euros, including man hours and analysis of micropollutants and things like that. So there's much more knowledge gained and yeah, insights. Let's go to another case study where we will be playing with the first full-scale installation in Sweden. So this is a plant for micropollutant removal. We are looking here at the Linköping digital twin at the right, and the real plant is at the left. So this is a plant that has recently been built in the framework also of the CW Pharma project. It's a plant of Technische Werken, and some of the people are also attending this webinar. And you can see that there is a side stream split, and then it is further dissolved in this first compartment. You can see exactly the same happening in the tree. Just like with a real process, a digital twin has water flows coming in, these blue arrows. It also has reactions taking place, described by a lot of chemical formula, which we have not really shown in this webinar. And you can also play with the plant controls. So that's also quite important and interesting. So let's go back to Giacomo's screen, and he will be outlining the Swedish plant.
Yes.
Wim, maybe I'll jump in again just before Giacomo starts. There's a question more on the process side of ozonation. What if our model predicts excessive bromate formation for the required API reduction? Do we ever discourage the use of oxidation based on this model, for example, for coastal use or anything?
Yeah, a very interesting question. Well, then we have to probably look at mitigation strategies. If bromide levels are really high or they spike from time to time, for example, they can be very well correlated with conductivity. This is what we have seen at a couple of plants. There are mitigation measures that you might be able to test. For example, the addition of hydrogen peroxide to suppress the bromate formation, which we have seen that works quite well when bromide is high. Again, it depends on the matrix, but it works quite well so far, we have seen. Or some other strategies, like the dosing of chemicals, other ones. But there are definitely things you could be looking at. Yeah. So mitigation strategies and the testing with the model is not something we will be covering now. We have done this in the last webinar, where the recording is available, and this was in the framework of the HRSD project in Virginia, the big water reuse project, SWIFT. So there they have bromide levels that are quite high, and still it's quite well working.
All right, let's go to the virtual representation of the full-scale plant of Linköping in Sweden. Here, as been explained, comes the effluent of the upstream treatment plant. You have the split to the side stream injection, where 10% of the incoming flow is directed. You inject the ozone, you join the mainstream again, and you let the reaction happen in the rest of the installation. Similarly to the previous demo, you can apply different control strategies. You can pick and try different controls without affecting the real plant. That's one of the main advantages of using this virtual tool. So in this case, we had a little less frequent measurements of the influent characteristics. That's why you won't see the very high dynamics and high frequency dynamics that you've seen before, but we can perfectly live with that. We have flow, we have total UVA, dissolved organics as well, ammonia, nitrite, and nitrate. And here what you see is the influent in black and effluent UVA concentrations and some measurements along. Actually, this is a year long. It's like summarized in about 30 samples here, but it's a year-long sampling campaign. And here is how the model goes through the data. We don't have to put much of hands in to do the calibration. We lived with an already previously calibrated model, actually. And here you can see how the gabapentin, one of the micropollutants of interest for this plant, for this territory, in the inlet and in the outlet, and the one in the outlet going through the measured data points. You can still, as I was saying before, you can still look at the conversion of the micropollutants that were here to see the list of interest for this plant, but you can also look at a much larger list that we have implemented there. So you can really have a large variety of micropollutants and all sorts of compound and intermediates that you can think of. The conversion, so both concentration and in conversion terms, and still the plant-wide variables. So plant-wide, what is happening to what is the delta UVA you are having along the year, rather than the overall ozone dose, and so on. All right, here's some gas flow, that's some process parameters. What is interesting to look at is a picture in an instant and in a single moment of the concentrations along the installation. So what are the concentrations here and there about like ozone in the side stream, where you have high pressure and high speed injection of your ozone? What is the concentration of UVA along the train in the side stream, and where you join again the mainstream? So you have an increase again of the concentration, but not only, and also about pH and micropollutants, and nonetheless also hydroxyl radicals. What is the local concentration of radicals? Where is that my radicals are produced the most, and where is that each micropollutant is depleted, and to which extent? Speaking of production, since we have many different pathways of producing hydroxyl radicals, you can monitor which one is the most productive way of for your installation, and in combination with your water metrics. That's very important. And what is the scavenging locally, and where it's happening mostly? These are all information that will lead to an optimal and can give all sort of background info to optimize your installation, or your design, or operation of your treatment plant. So this is all for this demo. I give the word back to Wim.
Okay, so there are some questions left, but we will reply them after finishing the PowerPoint, to not run too much over time. Okay, so we are heading to the end. For the people that really are very strict in time, we are heading to the end. We will do our best to go rather fast. So what we have done here is also some validation, additional validation. We have looked at what pilots and full-scale studies said in reality compared to what our model said in reality. So this is the reduction of pharmaceuticals as function of the ozone dose, DOC based. You can see that our model is nicely capturing the trend, which are the dark blue dots here. You can see that the same pattern is more or less happening. This is the average removal of 8 pharmaceuticals, okay? So average, on average, for example, with a 0.55 dose, you have around 80% average removal. You can also do the same with reduction of UVA, where we controlled the plant in our model at 30%. And we observed more or less 70% average reduction, which was very much in line also with both the full scale and pilot runs. So this is what Giacomo has been showing. I mean, you can look at ozone levels throughout the train, and you can see that specifically the hydroxyl radicals in a side stream, for example, but also right after injection, can be rather high. In this specific plant, the residual ozone was only very low, 0.2, and then you can see it disappears very rapidly if you go a bit further in the reactor. Giacomo has illustrated this, so these are 40 APIs, but yeah, of course we can. You can keep extending, just to show that all of them are both as again function of ozone and radicals. So this is the time the 1-year simulation we had, and the required ozone as function of time and also as function of control strategy. For example, the solid curve here is the DOC proportional, while the dotted line represents the UV, the delta UV control. Let's control at the 30% removal of UV before and after with 2 sensors or 1 sensor. And then you can see the corresponding API removal, the green line, and the corresponding UV removal. And in the controlled scenario, of course, you are just very stable at 30% because you are controlling your plants at this. And just hypothetically, what would happen in this plant if there were no nitrites? Well, you can see the same curves, these brown ones, dropping quite significantly. And these are the, let's say, the Bordeaux curves here, which are of significant lower ozone dose. So with a very low ozone dose, actually, you get the same API or pharmaceutical removal. In this specific plant, nitrites had quite an impact because the levels were quite significant. So this is really, really important. And if you look at effluent treatment, again, you can do a very easy comparative analysis in terms of ozone dose needed average and also the cost per hour in this plant. But of course, very much of this work and a very nice study has been done by the CW Pharma people. It has all been published and this is available. So we didn't, in this case, we didn't come up with the equations to measure the cost. We started from their equations. But you can see the impact on nitrites. It's easily 5 euros an hour less. Imagine you wouldn't have no nitrites. So we will now end this webinar. We will go to the conclusions, but we will take like 10 to 15 minutes more to answer questions and to have some discussion. So again, we have these 3 steps, which I discussed. And in the end, our goal with this model is to support all of these 3 steps. For example, by replacing piloting by a computer simulation. I'm not saying or claiming in every case this will be possible or this was the way to go, but for sure there are many cases where we could come to much better results in a shorter time and lower cost. We also think that ozonation systems can be better designed if you look at such dynamic modeling, taking into account the water quality and also flow rate changes. And then also what is very promising is having this model coupled with a real plant as a real digital twin. And a digital twin will give you in real time the bromate, but also the removal of your trace organics. And this is something we will bring in real life in 2021 at a couple of plants around the world, where we will have this AMOZONE model running in real time as a real digital twin. So what is the conclusion here? We are almost on time. Well, we expect, or at least our aim is to help removing significant practical, regulatory, and financial barriers with regard to the application of ozonation, but also we can extend it a bit to advanced oxidation. We are working on a lot of different activities. Yeah, and well, in this story, we didn't do it alone. This was quite some years of work for us to come with this well-validated model and all these equations. And we have a lot of partners, as you can see on the slides. So we want to acknowledge a lot of these parties on this slide, which were in one or the other way involved in the story. And our simulation team, specifically Giacomo, Roberta, Miguel, they do great simulation work on the ozonation side for our company. Okay, with this, we end the webinar. And yeah, I want to thank the moderators also and Giacomo for the presentations. Okay, so see you next time. And we hope to hear you via email or via Zoom. Nowadays, it's Zoom, right? Okay. Bye-bye, everyone.
All right.